Okay, so let's take a look at question 34 on page 501, which hopefully you've tried before watching this. So you have a job as a house painter. You climb up a ladder that's angled at 73 degrees at the bottom. It tells you that the ladder is 2.6 meters long, and it says that you are 3/4 of the way up. So you're up here. This is your FG person, and it's a uniform ladder, so this is FG of the ladder. This is F normal of the ground. Up here is F normal of the house, and friction at the ground will be going this way. And I suspect they're asking you for, assume the friction between the top of the ladder and the house is negligible. What must be the force of friction on the ground? Oh, so it's just asking for the force of friction, which is actually easier than asking you for the coefficient. If they're just asking you for the force, if we were to look at the x direction, some of the forces in the x direction, which will be 0, it'll be friction on the ground minus normal of the house equals 0. So the friction on the ground, which they're asking you for, is just going to be equal to the normal of the house. It means you don't actually need the normal of the ground. You can just find this using some of the torques, because that's how we can find the normal of the house. So let's do some of the torques. It has to equal 0. Remember, there should be a torque from every force starting out. So a torque from the normal of the ground, a torque from the friction on the ground, a torque from the normal of the house, a torque from the ladder, and a torque from you. Now you might be tempted to not pick your pivot point down here, because you might say, but wait, I'm looking for this force, the normal of the friction on the ground. And if I pick my pivot point here, it's going to cancel that torque out. But remember, we just found that the friction on the ground down here is equal to the normal of the house up top. So we can still pick our pivot point here. It'll still let these two torques go to 0. We can solve for the normal of the house, and then just say, oh, that is the friction on the ground. So this is my pivot point. Normal of the house is counterclockwise, which will be positive. Weight of the ladder and weight of the person clockwise, they'll both be negative torques. So positive, negative, negative. So R normal of the house, F normal of the house, sine theta normal of the house, minus R of the ladder, FG of the ladder, sine theta of the ladder, minus R of the person, FG of the person, sine theta of the person, equals 0. We're looking for this, so take the other two terms over, and they'll become positive. So R of the ladder, M of the ladder, G, sine theta of the ladder, plus R of the person, M of the person, G, sine theta of the person, divided by R normal of the house, sine theta normal of the house. Okay, and so now we can fill in our values. So it told us that it was a 2.6 uniform long ladder, which means the R for the ladder should be 1.3 meters. Told us the ladder's mass was 7.5 kilograms. G is 9.81 meters per second squared. And the angle at the base of the ladder is 73, which means the angle up here should be the complement of that, or 17, plus the R of the person, and it said 3/4 of the way, so 3/4 of 2.6 meters. Mass of the person was 55 kilograms, times 9.81 meters per second squared, sine of the angle for the person, which is between the R here and the F here. It would be this one again, so it should also be 17. Divided by R for the normal of the house, Starts here, ends here, so it should be 2.6 meters. And the angle for normal of the house is this guy, which should be equal to this guy, so 73. And then see if you can punch it in your calculator correctly. If you can, you should get 134.74 newtons. And that will also be equal to the friction on the ground. And you're done. If it had asked for the coefficient of friction, then you would have done the sum of the forces in the y to get your Fn. You'd have your Fn on the ground, your friction on the ground, and you could easily then find mu. All right. I also, on this sheet, wanted you to do numbers 4, 5, and 6 on the more torque questions. So number 4 is a sign hanging from a uniform beam. Okay, so number 4. So we have some kind of a pole. We have a beam going out. There's a guide wire coming down to the beam. Sign is hanging from a uniform horizontal beam, so the mass of the beam is 22 kilograms. It says uniform, so the FG of the beam is halfway along its length. And its length, its whole length, is 4.2 meters. There's a cable running from the end of the beam to the pole, making an angle of 50 degrees. And the sign, oops, imagine my beam's all the way out here. The sign is here, so this is FG of the sign. There's also going to be an F of the pole being put on the beam. So the first question wants to know what's the tension in this cable, FT. So pick your pivot point here so that this force goes to 0 and do the sum of the torques around this pivot point. Somewhere in here it must have told me the mass of the sign, 75 kilograms. Okay, so for part A, sum of the torques, and sum of the torques should be equal to 0. There should be a torque from the pole, but if we pick our pivot point there, it'll go to 0. A torque from the tension, torque from the weight of the beam, and a torque from the weight of the sign. Holding my writing utensil where the pivot point is and pushing in the direction of the tension, that'll be counterclockwise, and the two weights will be clockwise. Counterclockwise is negative, clockwise is positive. So it'll be R tension, F tension, sine theta tension, minus, oh, I did it the wrong way, minus, here and here, sorry, R of the beam, FG of the beam, sine theta of the beam, minus R of the sine, FG of the sine, sine theta of the sine equals 0. The thetas for the beam and the sine are 90, so these will go to 1. We're solving for F tension. Take the other two terms over. R of the beam, M of the beam, G, plus R of the sine, M of the sine, G, divided by R tension, sine theta tension. Fill in your values. The beam, uniform beam, so its full length is 4.2, so it'll be 2.1. The beam's mass was 22 kilograms times 9.81 meters per second squared. The sign is out on the end of the beam, so its R is 4.2 meters. Its mass is 75 kilograms times 9.81 meters per second squared. The R for tension, it's connected all the way out here, so between the pivot point and where the tension is 4.2 meters. And the angle is the angle between the R for tension and the F for tension. It's this 50 degrees. Okay, so punch these in your calculator. And when you do, you should get 1,101.32 newtons.